Good morning. The last session we were lost in space and talking about some kind of strange experiments in the orbiting space labs, and we'll pick up on that. Last time we were talking about an experiment to confirm the existence of the dark matter. See, I really had to think about that one, about the dark matter that makes up most of the universe. And we were talking about an experiment that would demonstrate the existence of this, or confirm the existence of this, by the production of positrons, and differentiating this from positrons produced by pulsars, and on the basis of their energy pattern. The scientists, particularly physicists, often do things in a somewhat strange way. They do a huge amount of theoretical work, fit in a lot of things together that are very mathematical, or I'll call it conceptual, without really simple math. And then they look to see, they make a prediction, and then they look to see if that prediction comes true. A statistician might call that Bayes' theorem on steroids, with an extremely strong prior expectation, and then you fill it in with a very simple finding. This was the case with the Higgs boson in CERN, where the entire theoretical basis of the standard model required something that would give mass to things, and the Higgs boson was verified, but it was really a very simple finding. Now, in the looking for dark matter, we're in a similar situation. We come up with some kind of explanation for the existence of dark matter. The existence itself is not in much question, or hasn't been in much question. Just if you look at the rotation of galaxies and try to relate that to the amount of mass that's in it, if you just look at the visual matter, it just doesn't come out right. So you have to think of there being some type of gravitation, some warping of space that's produced by some type of matter. And the dark matter concept shows that it's a lot more than normal matter, and that it does exist. And we're just trying to not say whether it exists, but the nature of it. So what we have in the original concept was a few funny terms, where first was saying, well, this dark matter didn't react much with anything else. So we ended up with the term Wimp, weakly interactive massive particle. And that stuck. And then the concept come up that this was a part of something that could be explained by supersymmetry, which kind of fills out the theory of all these particles. And and it turned out that it was figured that probably most of dark matter was made up of lisps. That's two kind of wimpy terms, lisps and wimps, but those are what we have. And lisps stand for least supersymmetric particle. And our visualization of this, and pretty well confirmed by these preliminary experiments of the incidence of the positrons and their energy pattern, is that it's something called a neutralino, and there are 4 of those, and one of them is the most stable, and this probably is the basis of either all or most of the dark matter out there. So the preliminary experiments strongly indicate the existence of this Wimp, Lisp neutralino, and stable neutralino at that. And so what we're hoping is that if the experiment can be continued for as long as 18 or 20 years, that this will solidly confirm this prediction. So I hope that this is able to be continued. This was a question. Another one that's very interesting and may or may not make it along the international space laboratories is a kind of strange one. It uses the experiment, the technique used in the Michelson-Morley experiment, which was used to see whether there was any ether and how the movement of our solar system relevant to that would demonstrate the existence of the ether. And it turned out that they were not able to discover this substance, ether. Now, what was that? Well, when we have sound waves in air, the sound is a vibration of the air particles, and then the sound wave gets transmitted. It doesn't get transmitted without it. If you yell in a vacuum, you're not going to hear anything because you won't get any vibration of the air. And so they were looking for this medium, and they couldn't find it. So the present experiment that was at least visualized, I saw it originally discussed about 3 years ago. It was kind of in a vague, undefined status. It got sharpened up a lot recently. And what they're looking for is whether space is continuous or granular. But granular on a very, very, very tiny basis. And so this would tell the nature of how impulses, how anything gets transmitted. So this, I really hope, gets on the orbiting laboratory, and whether it will or not, I don't know. We can be certain that if it does, it will be very interesting, and we'll see it in the newspapers. I haven't the slightest idea what value it might have, but science has paid its dues in the past, so I think we just need to do it, even if it's just for simple knowledge. And this one area of it I'm not too sure about. One thing that occurs is that if space has a bunch of rolled up, very tiny dimensions, whether that would affect the solution at all. So these need to be continued. The one on the granularity has to be continued in an orbiting satellite in which the space-time gets straightened out. One dimension issue disappears, and that's because the objects are weightless. See you next time.